Hello and welcome to another video on my channel. In this video I'm going to start looking at the basic math class in Java, which is built right into the Java JDK. So this class has basic math functions, and it only works for real numbers. Engineers have to deal at some point with complex numbers, which is a more advanced topic, and we will look into that in the next lectures. But for now, the basic math functions or the basic math class in Java is implemented for real numbers, and in JDK 8 you can find it under java.lang package. So it's in the core Java language. You can find the math class, and as we will look into this class further, this class cannot be instantiated, so the constructor for the math class is private, and it contains static methods. So they are class methods. You access them via the class name. So those are not instant methods, they're just static methods. And the math class actually has calls to another class, which is called StrictMath. And StrictMath, I believe, uses mostly native libraries. So it has interfaces to C++ libraries which are natively available for the operating system, Mac OS or Windows. And you can do that in Java using the Java native interface. And as I mentioned, the math class only works for real numbers. Okay. Now, typical math functions are exponential and logarithmic functions, absolute value of a real number, minimum of 2 real numbers, maximum of 2 real numbers, ceiling, which is the nearest integer that is equal or larger than x, floor, which is the nearest integer that is equal or less than x. And there are some basic trigonometric functions: sine of x, cosine, tangent. I believe cotangent is not implemented because cotangent is just the inverse or the reciprocal of tangent. So cotangent is basically 1 over tangent. And I'm not sure if the inverse of trigonometric functions are also implemented. We can check it. We will check to see if these functions are implemented or not. Now you can add your own new functions, and what I typically do, I define a class called more math or math utils, something like this. I personally like if you just want to define more functions, it's better to have it as a more math class. That's a more appropriate name for it. Other stuff that usually engineers do when you're dealing with differential equations or Laplace transforms, Fourier transforms, you have unit step function, delta function, for example, delta of x or x of at some point a, for example. So this is a delta function. And hyperbolic tangent, cotangent, hyperbolic sine, cosine, and the inverse of those functions. And as I mentioned, all the math class has all the methods and all the fields are static. So math class, I believe, has 2 fields that are static fields, which is just the definition of pi, number pi, and number e, these 2 numbers. And since they have all static methods, we can just use at the top of a class, we can just define use the import static, and then we don't need to each time write the math dot something. It's just you write the name of the function. That's the tip that we can usually do. So let's head back to Eclipse and look into the math class. Now if you remember, I already downloaded the mathlib library from the GitHub, and this is basically a collection of all the Java files that I could find online. Some of the files I wrote them myself. There's a lot of archived libraries, math libraries, and these are basically all that is available for Java, at least most of it, and we will look into that. But for this video, I'm just going to create a simple Java project and call it math demo, and I'm going to use Java Standard Edition 1.8, no dependencies, only the Java library, and okay. Alright, now here I'm going to go to Java runtime. This is the basically where the core Java is, and in the runtime rt.jar in Java under the lang package, this is the core Java language, we have the math class. Okay, now if I open it, I basically decompile it. And if you're curious how I decompile this, there's a plugin for Eclipse. If you go to about Eclipse, there is this plugin called ECD, Enhanced Class Decompiler. And if you haven't installed it on Eclipse, what you can do, you can just go to Eclipse Marketplace, for example, and search for Enhanced Class Decompiler. Enhanced Class Decompiler. And then when it finds it, you can just download and install it. I've already installed it. So after you do that, you have to go to the preferences under the file association. Make sure that all the .class files and the .class without source, the default is the class decompiler, not the class file viewer. For the .classes without the source and the .class files, for these two, make sure the class decompiler is the default. Okay, after you do that, you can just right click on a .class file and it just decompiles it and shows the actual code. Now let's just look at the outline here. You see the math class is a red square. In Eclipse, it means it's a private method, right? Constructor is basically a method, and it's private because it's red. And the C label here means it's a constructor. Okay, so the constructor of the math class is private, so you cannot instantiate the math class, and it's final. What does it mean? So when it's final, it means you cannot extend this math class. If the final was not here, you could in theory extend it, but because this class is final, you cannot extend this class. So two static fields which are public because they are green circles, empty circles are fields, field circles are methods, right? And they're green, so they're public, and they're static, they have this static label, and they are final, so they are constants and you cannot reassign them. Okay, and then there are a bunch of methods. Sine, so this is the sinusoidal function, the trigonometric function. As I mentioned, the sine function here just calls the StrictMath, and the sine method in the StrictMath class. So if I hit the control and then click on StrictMath, this is also final. And as you can see, the StrictMath basically doesn't implement anything. It just calls the native classes. So StrictMath calls the native methods from the operating system. It doesn't have any implementation of the actual functions. For the cosine, the same things. It calls the StrictMath, and then tangent, arcsine, arccosine, arctangent. Notice cotangent is not implemented because by definition cotangent is just 1 over tangent. Okay, and arc cotangent is pi over 2 minus arctangent, so you don't need to implement both arctangent and arc cotangent. So if we go back to the presentation, these the inverse of trigonometric functions are also implemented. Okay, we have 2 radians and 2 degrees. These are for converting angles, which is useful to have. We have the exponential and logarithmic function. And we also have log 10. So the difference is that log is the natural log in base E, and again it calls the strict math, and log 10 is in base 10. Now if you want to implement your own log, let's say log 2, log 5, you have to use the base conversion. And then we have the square root, the cubic root, CBRT is the cubic root, IEEE remainder, so you can read the details what this exactly is. The ceil function, the floor function, the rint function, arctangent 2, which gives you the coordinates, basically tells you where the actual angle is so in the 2D plane we have 4 quadrants, and this tells you exactly where the angle is. The power, so if you want to raise number 8 to the power of b, you just use this POW, rounding a float, rounding a double. Again, all these methods are public, but they are static. So math, if you look at the outline, everything is static here. And then we have a random number generator. So this is a class, and this is an inner class, okay? And this inner class basically just creates a random object. And why did they do this here? Because then there's a function called rand. And with the random method just calls this random number generator, this class, and it basically calls the next double method. So it creates, every time it creates a new random number. We have addition in the exact sense for integers, for longs, subtraction in the exact sense for integers. So the thing is that when you have two integers are 32 bits and longs are 64 bits, so when you add them there's a chance of overflow and the result will not be correct. So I've never used these two, add exact, but I assume they are going to somehow take care. Actually, they don't take care of this overflow, they just give you an exception. So they warn you that something went wrong because there was an overflow, okay? Normally you don't use this because the integer numbers that we deal with, engineers deal with, they're not that big. And then we have multiplication again for the integers and longs because of the overflow, increment, and again all these exact methods, they give you an error or warning or exception. Basically they throw an exception saying that okay, some overflow happened and you have to take care of these exceptions. Decrement, negate exact. Remember Java, for the integers, Java uses the 2's complement representation of binary numbers for signed integers. If you're not familiar with 2's complement system for signed integers, you can just Google it or go to Wikipedia. We have toInt exact, conversion from long to integer, floor division, absolute value of a long, float, a double, maximum of 2 integers, maximum of 2 numbers, and now we have 2 private static fields. So they are red squares are private, and because they are not a field square, the inside of the square is empty, it's white. So that tells me that it's a field, not a method, right? So a static field, private static field. Floor to raw int bits. Again, these are things that I personally have never used. Maximum of 2 floats, maximum of 2 doubles, minimum of 2 ints, minimum of 2 longs, 2 float numbers, 2 doubles. These functions that I forgot what these are. Signum, this is the sign function, and it returns -1, 0, or +1. Signum or float. Hyperbolic functions, I actually wasn't sure if these were implemented or not, so hyperbolic functions are also implemented. Sine, cosine, tangent. Again, cotangent hyperbolic is not implemented because it's just 1 over tangent hyperbolic. So hyperbolic functions are also implemented. The basically square root of x squared plus y squared, or the distance of a point in the 2D plane xy from the origin. It's also implemented, and it's interesting that instead of just simply writing the expression, they're calling the native functions from the StrictMath. And I'm not sure if that's native thing, and I'm not sure if that's for better efficiency. Actually, I doubt that, because usually native interface is not the best way or the most efficient way to do it. That's interesting. Exponent, sine, get exponent. I believe these are for the floating point representation. You can just get the exponent, and the Java uses the IEEE standard for the floating point representation of numbers. Next after, next up, I have personally never used this. Scalp 2 to the double. So these are fields, static fields, and the rectangle sign shows that the access modifier is the package level access. So they don't have any modifier, which means they have the default access modifier, which is a package level. And these are power of 2. Power of 2, again, this is a method. These ones that have the inside is empty, these are fields, and these field triangles, these are methods, and they have a package level access modifier, and they are static. Alright, this was the whole math class and the StrictMath. So StrictMath basically calls the native libraries, and the math class basically calls the StrictMath. So math class doesn't really have any actual implementations. Now let's go back to the source and create a simple class. Let's call it the demo1. I'm just going to create a main method. And in the main method, I'm going to, so as I mentioned, you can, everything in math class is static. So you can use the math class name to get the values or fields or methods, and then system.out.println A, for example. If I run this, I get the value of the E. Similarly, I can do pi, for example. And then let's say I define B math.sine of A times math.cosine of math.exp of A. Now, as you can see, having a lot of functions inside each other is make your code really not that much easy to read if you need to call the math class every time. So what you can do, knowing that all the fields and methods inside the math class are static, you just use the import static math, basically java.lang.Math, everything with this star. And then I do not need to use this math dot, and then B, and this should work, right? So if I'm just dealing with a lot of these functions inside each other, I just import everything as a static import, and then I don't need to write the math dot every time I want to call one of these, and that makes life much easier. Now, another thing that I want to basically talk about here is the double class. So mostly in engineering, so first of all, numbers in Java. There are some primitive numbers: byte, short, int, long, float, double. Okay, 8-bit, 16-bit, 32-bit, 64 bits. These are integers, and then we have floating point numbers, 32-bit and 64-bit. And the default for the floating point is double. The default for integers is int. Okay? And there are things about typecasting, upcasting, and downcasting, this kind of stuff. I assume you already know these. But in Eclipse, the compiler always tells you and warns you when something's not safe, and you have to deal with those. But there are also wrapper classes for primitive types: byte class, short, integer, double, float. Now these wrapper classes, specifically the double class, has some interesting constants, and a special constant called NaN, not a number. And not a number is usually useful when, for example, let's say you want to solve an equation, but there is no solution for that equation. So you can either return null or NaN, not a number. And most people usually return not a number. It's better, it's safer than returning a null, because you may run into the null pointer exceptions in Java, which can cause problems, right? So returning NaN is always a safer choice. And double also has a method called isNaN, so you can check whether or not a number is NaN. Okay? And there are also useful parsers. So parser is basically taking a string of a number and converting it into an actual number, okay? Primitive type. So this is a string of 23, and I can convert it to integer. Now I can use the double parser to, for example, parse an integer, and it converts it into double. And there are also other classes like big decimal that I personally normally don't use, but there are some use cases for these, but if in your work you typically work with double numbers, you don't need to worry about big decimals. Okay? All right, now let's go back here. Let's say A equals the double class, which double A. So A is a primitive type of double, and I can call the wrapper class double. Max value, mean value, let's say max value. And double has a floating point representation, and it's the IEEE standard. Print A. Okay. System.out.println A. It's a 1.79769, etc., 10 to the 308. Now mean value, obviously it should be, I believe it should be the negative of this number, because doubles have no, actually it's not the negative, it's something very small. And we can also look at the integer, for example. Int b equals integer dot mean value, and print in minus 21, 47, 48, 36, 48. Okay, and let's look at the parsers. So let's say a string s1 equals 23.1, and double s2. I want to convert this string into a double primitive. So what I can do, I can use the parser that is already inside the double. Parse double s1, and then system.out.println s2. As you can see, now I have a primitive type double with a value of 23.1. Now what happens if we cannot convert to double? Obviously it throws an exception telling you that it couldn't successfully convert this expression into an exception. So what we actually could do was surround this with a try catch. Try this, or maybe I could just use the autocomplete. Try catch. So try this, and catch is number format exception. Number format exception, instead of just printing the stack trace, you just say system.out.println could not convert to double number. Obviously we have to also print it in the terminal when we're doing the try. Could not convert. So when you're developing a software, you always have to, you should always handle the exceptions instead of just printing the stack trace, because that you have to put some meaningful information for the user. Alright, thank you very much. I guess this wraps this tutorial on the basic math class and math functions in Java. In the next lectures, we will look into other important topics in scientific computing with Java. Thank you very much. Please share and subscribe. And I'll see you next time.